Welcome to solverfy.
Since we know, for part A, since we know that the kinetic energy is equaling 7.5 mega electron volts, and this is going to be much, much less than the mass of the alpha particle times c squared, we may use the non-relativistic formula. So the momentum would be equal to the square root of 2 times the mass of the alpha particle multiplied by the kinetic energy. We're going to be using then equation 3843, and we can then say that lambda, the wavelength, would be equal to Planck's constant divided by the momentum. This is going to be equal to Planck's constant times c, the speed of light, divided by the square root of 2 times the mass of the alpha particle times c squared times k. And so we can say that here, this is going to be equal, rather, let's get a new line. The wavelength would be equal to, we can say that 1,240 mega electron volts femtometer instead of electron volts nanometer. And then this would be divided by the square root of 2 times 4 atomic units, which is essentially the mass, or the mass of the alpha particle, multiplied by m. This would be the mass of the, this would be the alpha particle. However, now we are going to also substitute in for the, essentially the energy per atomic unit. So this would be 931.5 mega electron volts per atomic unit. And that's where the mc squared comes from. That would be essentially the energy per atomic unit times the number of atomic units. And then multiplied by, again, 7.5 mega electron volts. This is simply the kinetic energy. And we find that the wavelength is 5.2 femtometers. This would be our answer to part A. To part B now, because the wavelength is equaling 5.2 femtometers, and this is much, much less than 30 femtometers, we can say that the wave nature of the alpha particle does not need to be taken into consideration. That is the end of the solution. Thank you for watching.